Alright folks, this video is going to do some review of interval notation to talk about domain and range for functions and other relations, and then also talk about using our graphing calculator to create a comprehensive sketch. With that in mind, make sure you have a graphing calculator handy and then also a straight edge for those graphs. To begin, we're just going to review what interval notation looks like. So you were first introduced to talking about infinite sets with set building notation. That's what you see in 1, 2, and 3. What we're going to do is first graph the solutions and then use that graph to change it to interval notation. Okay, so first up, we've got a compound inequality. This is an AND. If you see two here and they're kind of smushed together. But if you read this, it says the set of all x's, that bar is such that this one says x is greater than -1 and x is less than 4. Essentially, this just means that x is between -1 and 4. So what we're going to do on our number line is just put the numbers we need. Okay, so we've got -1 and we've got 4. You don't have to do any more than just that. And we're going to shade the solutions. Okay, so -1 here doesn't have an underline, so it's not really included. We'll put a circle there to represent that. Same thing goes on 4, and then since it's between, we'll just shade between. Now, how we write this is in interval notation is using parentheses or brackets to decide whether a number is included in the set of our solutions or not. So we decided this -1 was not included and this 4 was not included, but we want all the numbers in between. In general, interval notation will always go low number, comma, high number. So our low number on our solutions is -1. Our high number is 4, and parentheses go with our open circle to say we don't want to actually include them. Next up, we just have one number. Okay, so we're putting on our number line 3 here, and we want all the solutions that are greater than or equal to 3. So this time 3 counts, so we want to put a solid dot on 3, and then we want all the numbers on the number line that are larger than that, so it'll point exactly the direction you see. Right? So low number, high number for this one to switch to interval notation will look a little bit different because there's an arrow involved. Anytime an arrow is involved, we're going to include infinity or negative infinity based on where we are on the number line. So here, our low number on the left is 3, comma, high number, it's headed towards positive infinity. With infinity, since we can't actually reach that, it will always get a parenthesis. But with our closed dot here, we're going to put this square bracket to say that 3 is part of our solution set. This last one has this strange symbol here. It means an element of, so x is an element of the real numbers. I'm just going to put 0 on here since we don't have an actual number value there, but the real numbers is everything on our number line, so we'll go ahead and shade the whole thing. And because we're shading the whole thing, we've got a left pointing arrow and a right pointing arrow, so this starts at negative infinity on the left and goes all the way to positive infinity on the right. Remember, infinity is never included, so we'll put parentheses around both of those. Okay. Next thing we're going to do is work backwards. Okay. With this, we're given interval notation, and we want to change that to set builder. Okay, so remember this is the lowest number, then the highest number. What we're going to do is start out with the set of x's such that, and then we have to think here. Because there are two numbers here, we want to say that x is between them, between 5 and 10. Okay, if it helps, you can draw yourself a little number line here. 5 is there, 10 is there. And because it's between it, we've got open on both sides. Now, this looks a lot like our notation for the problem that we just did on number 1. And so our set builder notation is going to look very similar to what we had here. Anytime that your graph is a segment, instead of looking like a ray, we want to make sure that our x is in the middle. But you'll notice both of these arrows are pointing to the left. As long as you go lowest number first, then highest, that will always be the case. Okay? Because like I was showing you here, this says x is greater than -1, even though that -1 is pointing to the left there. Okay? So on this one, we want to go low number. For us, that's 5. X goes in the middle. High number is 10, and then our arrows always go to the left. You just have to decide if those numbers need to be included, so if we need to put an underline there. In this case, we decided no, so that's it. Okay, pause the video and try out number 5. The only thing different about this one is we want to make sure that that -7, since it has a bracket, gets included. So your arrow should have an underline there. But on the right-hand side, with 4, we won't. Okay, again, if it helps to draw your number line, please do that. Okay, we'll have a closed dot on the right, open on, or closed on the left, excuse me, and open on the right to take care of that. Alright, when we have interval notation with infinity involved, okay, what we're going to do is always say x is to the left of the number we're given, or x is to the right of the number we're given. So start out with the x such that, and then we're going to compare x to the number 8, and just decide, would that be to the left of that, or to the right? So -infinity is to the left on the number line, so we'd point to the left, and there was a bracket, so included. Graphically, that's a solid dot here, and -infinity is lower, so it's everything that direction. Okay? If the infinity is on the left, we're going to point to the left. If the infinity is on the right, you're going to point to the right, and that's it. Next thing we're going to do is look at a relation. Okay, a relation is just any set of ordered pairs, and decide whether, or decide the relation's domain, the relation's range, and then whether that relation is specifically a function by writing yes or no. Okay, so we're going to use interval notation to talk about the domain and range, like we practiced just a little bit ago, unless we're dealing with a discrete set of points. So like number 7 here, we've got specific points. There's 4 ordered pairs there, so we can do the domain by just listing all the x values and the range by listing all the y values. We only want to use set builder notation or interval notation when we have an infinite amount of values in the domain and range. Okay. So first step, let's talk about domain here. Remember, it is the x value, so we will just list our x values since we only have 4 of them. And I'm just going to go in the order that you see them. So 5, then 3, then 4, then 7. What's really important for domain and range, when we're talking about these things, we're just listing the x values that show up, or the y values that show up on your graph, or in your definition of your relation. You do want to be careful to never repeat yourself. If a y value or an x value shows up twice, you don't want to write it twice. Okay, we're just listing the unique values that show up. So for the range, we're doing the same thing with our y's. So it looks like 1, 2, 9, and 6. Now, if we have a graph, we can decide whether the relation is a function by using the vertical line test. But since we don't here, we have to use the definition. And that means we want all the x values to map or pair with exactly one y value. The easiest way to kind of think about this by looking at our set is just ask yourself, do the x values repeat? Okay, if they don't repeat, you're good to go. That's a function. But if they do repeat, you're in trouble. Okay, so here, all of our x values are unique, so this is a function, no repeats. Okay, let's look at number 8 here. We're doing domain and range again, but now we're looking at a continuous function here. Okay, so this is a discrete, we decided, because we could count all the numbers, but this one is continuous because all those points create this curve here. And so we're going back to interval notation. We always want to go lowest to highest with your interval notation. X is from left to right. So here, even though we can't see it, this is a parabola shape that we know goes on forever to the left and right, and then on forever going up here. So with x's, the lowest thing on the left is this arrow, so that's negative infinity. The highest thing on the right is the arrow again, so that's positive infinity. Alright, then we're going to go to the y values. We're going to go bottom to top here. It does give us in this corner here, the x is 2 for this ordered pair, and the y value is 1. If we didn't have that, and your graph isn't super clear, you're just going to take your best guess at what that value is. We'll get to some examples like that here in a little bit. So our lowest value on the y's here is that 1, and it is a point on the curve, so we want to include it. And then we're going up from there towards positive infinity. Because this graph passes the VLT, this is a function. Okay, remember the VLT, all we're looking for is if we draw a vertical line through the graph at any place, it will not ever hit that vertical line in 2 places. Okay, so this one passes, we only hit it in one spot no matter where we draw it, so it is considered a function. Alright, number 9, we're going domain, low number, high number for the x's, and then range, low number, high number for the y's. Okay, pause the video and try this one. Okay, going left to right, left here we see an arrow. Arrows will always mean infinity. You just have to decide positive or negative. Okay, pointing to the left, we've got negative infinity. And then the x value stops right here. Okay, so that's the x value of 0. It is included on the graph. And that's it. When we move to the y's, we're starting from the bottom going up. First thing I hit is an arrow, so that's negative infinity again. Going all the way up, and then we're looking at the y value, and that stops at negative 1. Again, included, so we're using a bracket. This again passes the VLT, so we say yes, this relation is a function. Okay. Number 10 is the first time we see on our graph asymptote show up. Looks like we have a vertical one at x equals, watch your scale, here's counting by 2, so x equals 2. We've got a horizontal one at y equals 4, and we're going to use those to talk about domain and range. Okay, so because there are 2 different chunks in this graph, we're going to do 2 different chunks for our domain, and the same thing with our range. So, going from left to right, first thing I see is this arrow, negative infinity, and I'm going to follow it along until I hit this vertical line at 2. Now, an asymptote is where this graph is approaching that number 2, but it isn't actually touching it, as you can see. So we'll say it gets really close, but we'll use parentheses to say it's not included. So anytime you see an open circle on a graph or an asymptote, we're going to use those parentheses. Then we pick back up right on the other side of this, so we'll put a U in between here for union to talk about that second piece. This piece picks right back up where we left off, so we're going to start at 2 again, but not included, and then keep on going to the right towards infinity. With that in mind, our y values are going to look very similar. We're going to start at the bottom and move upwards. So at the arrow, we're going to write negative infinity. Moving upwards, this is the y value of 4. Same process here, we want to hug it with parentheses and start right back up at 4 where we left off, all the way to infinity. This again will pass the VLT. It looks like here we get a little steep, but it's decreasing but still moving towards that too. So it's not vertical at any point. This does pass, so it is considered a function. The next 2 problems are probably the hardest parts on this this practice worksheet here, but I do want to have you pause the video here and see what you can do, because if you can handle these two problems, then you shouldn't have any difficulty at all with your homework. Alright, let's take a look here. First up, we've got a few different pieces here, but let's go left to right and talk about what's going on. So from the left, we've got negative infinity. I have to stop at -3 here, this point, because it's an open circle on the dot, and that means we have to not include it. And then we want to keep going right past at -3 all the way till when we hit 3. Now, if you look over here, 3 is included in this first one. It's not included in the next one, but then directly after this open dot, it keeps moving, and so I get everything to the right of 3. Because 3 was included in this first branch, I don't have to stop. I can say it keeps going from this -3 all the way past it, because at this point, this intersection here, one of them was included. Okay, it just has to be covered somewhere, and then you don't really have to stop. Okay, let's do the same kind of process with our y's. We're starting at the very bottom. The lowest thing here is the 1. It's not included, so open circle, but past that, if you just keep on this one, this arrow, even though it stops kind of low, keeps going forever and ever. So it doesn't matter what's going on over here, because the y value of 3 is covered all the way through here. It doesn't matter that it's open at that one point. Okay, so 1 to infinity for our range. This does pass the VLT because at this point it's only included in one spot. So we're good to go to call that a function. Number 12 is similar to the one we talked about on number 10 with the asymptotes. Okay, so we have a vertical one at x equals -2. We've got a vertical one at x equals +2. And then we've got one at y equals -4. Okay, so left to right first, we're starting at -infinity, and we get all the way to that asymptote. We stop, but pick up right after. Then we're from -2 to 2 in that next chunk. And finally 2 to infinity to cover all of the x values. On the y values, we've got a little bit of work to do here, because the bottom chunk goes from -infinity to -4, but this is the first example where it doesn't pick up right where you left off. There's this gap in the y values, in the vertical part of the graph here, that we want to skip over. It doesn't pick back up until right about here. Now, you'll notice I put an approximately here because the graph isn't super clear on what that value is. Looks like it dips below the x-axis, but I'm not really sure by how much. So in the case of something like this, I want you to say just approximately and give me your best guess. Okay? We want to say still here that, and I messed up on this, so let's fix it. Okay, on this one, because that loop here is solid, we do want to say that it's included. Okay, so we want to put a bracket here. But then we're going up from there all the way to infinity to finish out the graph. Next thing we're going to do is just graph some of these types of equations from their function. And here are some rules that we're going to follow every single time. Okay, so when we're talking about sketching, and this should be familiar to Algebra 2, we're going to have a grid, and we'll put our dimensions on the outside of the grid based on the appropriate window for our function. We want to make sure the x and the y-axis is graphed, so we have an idea of where we are floating in space. And then all critical values are going to show up. Okay, so we want to label any x-intercepts and y-intercepts if they're there. Endpoints, this is for like a square root function. Okay, it looks like a graph like that. Okay, so an endpoint would be important, or maximums, minimums if they occur. If we have any graphs with asymptotes, we're going to label those. And then we won't put any arrows on them, even if they go on forever, kind of like here. We're only going to choose a window of the viewing, so we want to just say that this is almost a screen clipping of our calculator. Okay, so This is where we'll need our graphing calculator and a straight edge to take care of a couple examples here. Okay, so we just kind of talked about the square root function, what it looks like. If you recall from Algebra 2, and it's okay if you don't, but you were given a purple note card that dealt with a generic function, and it looked kind of like this. You had an a value, then bx minus h, and then plus k, where these grouping symbols just meant whatever parent function you were dealing with. So for us, this is a square root, and then this minus 2 talks about a translation. Specifically, if you see a minus 2, that would mean 2 to the right. If you see something on the outside, that would mean up or down. And then those a and b values tell you about reflections and also stretches or compressions in your graph. Okay, so that was really quick, but we're going to do calculator work, so I didn't want to spend a lot of time on that. Just mention this really means 2 to the right from where it normally is. Okay, so what we're going to do here is practice on our calculator with some stuff here. So I want you to go to the y equals, clear out anything you have. Last chapter we had the plots on. We want to make sure they are turned off for what we're doing today. Okay, so I just went up there, highlighted it, and hit enter. You can also go second y equals to make sure all of your plots stay off there. Going back to the y equals here, we want to type in this equation that we were given. So ours is the square root of x minus 2. And then I'm going to go take a look at the window, and we want to change it back to a 10 by 10. The easiest way to do this is zoom and then 6 for a standard 10 by 10 window. Now, we may adjust this window based on what's nice to see our graph, all of its important parts, and make sure that our graph is the focus of it and we don't have a bunch of extra wasted space. Okay, so as you can see here, there's a bunch of wasted space here that I don't really need. Okay, instead what I want to do is focus only on this chunk here. But it looks like I've got an important piece here that's an end point and also an x-intercept, but really there's nothing else happening in terms of a maximum or minimum. So what I'm going to do is put my x-axis way over on the left, my y-axis way towards the bottom, and then graph my picture from there. Okay, so with your straight edge, let's do just that. Go ahead and up and down, put it way on the edge, left and right, way on the edge. And then what we're going to do here is label whatever we want to count by. Now, I decided that a 10 by 10 wasn't a good idea and that we move this over. So instead, you'll notice I'm going to the left 1, and I'm going to the right 1, 2, 3, 4, 5, 6, 7, 8, 9. Same thing, I'm going down 1 and I'm going up 9. So if you want to adjust your window to match that, you can say -1, 9, and then same thing on the other side, -1, 9. Okay, your calculator doesn't necessarily have to match what you're graphing on your paper. We just want to make sure what we're putting on our paper is a good fit for our function. So here's how we'll label this. We don't want to put tick marks and the scale on the inside. We're putting the dimensions on the outside. So our lowest number was -1, highest number was 9. Same thing going here, lowest number was -1, highest was 9. Okay, we only have one important number, and that's this right here. Okay, we decided that instead of 0, 0, we've been shifted to the right 2, so that should be the ordered pair 2, 0. To test that, if you hit trace, you are allowed to type in any x value you want, and it'll kind of test if you're at that endpoint or not. So if you test 0 and hit enter, okay, it comes up here as nothing, okay, because that was over here. We want to type in 2 for our x value, and there I'm at y equals 0. Okay, so whatever your endpoint is, test it, type it in right the first time, 2, 0, and we're going to plot it on our graph. From there, our shape just kind of goes up and towards the right. What I'm going to do is go ahead and find out wherever this ends. It's not critical to the graph, so I'm not going to label it, but so that I don't graph something like this when it should be down here or way up here, what I want to do is just get where I'm supposed to end in terms of this scale so I can end up in the right place. So our edge was 9, so I'm going to trace 9, hit enter, and I'm supposed to end with about 2.6. So on your y-axis, 2.6 is about here, and then that's where I have to end my little curve. Okay, so you just arch it up until there. Again, I'm not going to label that because it wasn't critical, but I'm also not going to put an arrow because for these sketches, we're never going to throw arrows down. That is our comprehensive graph for this one. So our job now is to decide if the relation is a function. If it is, we'll give domain and range. If it's not, we won't worry about it. Okay? So here we're passing the vertical line test, so we're going to say yes, it's a function. Domain, starting from left to right here, the lowest number is 2. It's a solid dot, so included. And then we're going to the right, even though this screen only shows up until 9, we're going on forever past that. So we'll say infinity. With the y values, we're going from the bottom up. The first value we hit is 0, including that, and then on to infinity, even though it gets there a lot slower. Close that, and we're done there. Next graph is a little bit more interesting. Okay, notice that we have x in the denominator. This is not necessarily a graph that you're familiar with, but because x is in the denominator, you will have asymptotes in this graph. Okay? The reason for that is, if we think about this, I'm going to go ahead and rewrite it, and x squared minus 4 is a difference of squares. X plus 2, x minus 2. And what that means is, if I plug in a -2 here, that becomes 0, and I can't divide by 0. That's a restriction in the domain. Because it's an x value, that doesn't work. Same thing over here. If I put 2 in there, that causes problems because then I'm dividing by 0. Okay, let's go type this in our graph, and then I'll show you what the graph looks like and how these actually show up. What's really important is anytime you have a fraction, you make sure that you include the numerator and the denominator in parentheses if there is more than one term. So for us, we have to say 1 divided by, and then take the quantity, x squared minus 4. Okay, so parentheses on both sides there. And then I'm going to go back to a 10 by 10 window. So I'm going to hit zoom 6. Okay, it looks pretty strange here. But what I'm going to do is show you what happens when I trace that 2 and that -2 that we were just talking about. Okay, so I'm going to hit trace and 2. Notice it shows up blank. Okay, kind of like I showed you earlier accidentally. Blank means it's undefined at that part. So undefined here is the vertical asymptote that is showing up between these two branches. Okay, it won't be graphed on your calculator. If I do -2 and hit enter, the same thing happens because I've got 2 asymptotes in this case. Again, it looks like I have a lot of extra space over here and over here that I'm not worried about. So we're going to cut this down to probably a 5 by 5 instead of a 10 by 10, so we're really focusing on the important parts of the graph. So go to your window for me, and let's change everything to 5s. Okay, so -5 to 5 for your x's, and the same thing for your y's. And then hit graph. Now we can see more clearly what's going on, and we can graph this pretty well. First step, now that we've decided this is what we want to go with, is put our x and y axis on. It's symmetric, so we're going to go right down the middle here. So go ahead and draw that going to the left and then up and down. Remember, our dimensions are going to go on the outside. So 5, -5, 5, -5. With our asymptotes, we're going to dash them. Okay, so it was at 2 and -2 we decided. So a dashed line at both of those. And what we're going to do with these is make sure we label them. So vertical asymptotes, x equals, so we got x equals 2, and then we got x equals -2. Now, what you don't notice here, but is actually happening, there's also an asymptote at 0, going left and right. If you see, it looks like those branches are sitting right on top of the x-axis. That is also an asymptote. You don't necessarily need to dash it because you're on top of the axis itself. What you do need to do is label it. So it's y equals 0. That tells me you know it's there. Okay. From there, what we're going to do is talk about critical points. X-intercepts, y-intercepts, max-mins. Those are what we're looking for here. On these branches to the left here and to the right up top, we don't have any critical values because it never hits the x-axis. However, if we didn't graph at least one point, we wouldn't be accurate. You have to have at least one point labeled on each branch of your graph. So all we have to do is pick any point that's to the left of this asymptote. I'm going to trace -3 and see if it comes out nicely. Okay, -3.2, that's pretty nice. Okay, so I'm going to plot that one. So -3.2 is about here. And then I'll go ahead and draw that curve. Okay, start at the asymptote, end at the asymptote, and it's -3, 0.2. Moving over to the middle, we do have a critical value. It's the y-intercept. There's two ways to find this. Okay, with a y-intercept, you can just think about the ordered pair. A y-intercept is 0 something, so we can just trace 0. You can also look at the equation and plug in 0 by hand, and that's 1 over -4 or -0.25. Okay, let's graph that one. Again, start at the asymptote, go through your point, end at the asymptote, and let's label that one. Fraction or decimal is fine with me as long as you're not rounding. If you are rounding, we want to say approximately. Last one over here, we're going to pick a point as well since there are no critical values. So to the right of 2, I'm going to trace 3, and that's 0.2 because of the symmetry in my graph. Start at the asymptote, go through the point, end at the asymptote. And that is everything I need on this graph. Okay? I want you to pause the video and tell me whether this is a function, yes or no, and then if yes, give me the domain and the range. This was a yes. Domain here is -infinity to the asymptote -2, picking back up at -2, going to +2, and then 2 to infinity. The range, kind of like what we talked about last time, we have to stop right there. So it's -infinity to the -0.25, but that's included on our graph. Then union, we're picking back up not until the asymptote, and because it's an asymptote, we're not going to include it, and then say 0 to infinity. So a little bit tricky there. But that's all for comprehensive sketches. If you do have any questions on that with your homework, please come see me. The last thing we're going to review is function notation. This should be really quick, but it's just a reminder of how things work. Function notation is read, this is a g here, so this is the value of the function at t, and it's given by t squared minus 5. So what we want to do is find the value of the function at -7, and that's just in the spot of t, so what we're going to do is put it in the spot of t on the other side. So t is getting squared, we're going to square -7, and then subtract 5. So for us, that's 49 minus 5, which is 44, and we're done. Essentially, this means the ordered pair -7, 44 would show up on this parabola. Okay. Part B is asking a slightly different question. It says find the values of t such that g of t equals 12. So this time we're solving for t instead of figuring out what the g of t equals. Okay. We're told that the g of t equals 12. So how we set this up is replace the function part with g of t. So that's t squared minus 5, and then set that equal to 12. In order to solve for t here, we have to add over the 5, and then we get 17. Taking the square root, we've got t equals plus or minus the square root of 17. We can't break that down, so that's our final answer. Okay, some problems like this you may have to factor to solve, get it equal to 0 and then factor. This one we didn't have a regular t, so we could solve it using the square root method. Domain and range, we want to think of the graph of this guy. If you're not familiar with your parent functions and that minus 5, you would need to use your calculator. T squared is a parabola, just like x squared. Minus 5 shifts it down 5. So with this, the domain of all parabolas is negative infinity to infinity. The range, since I went down 5, is negative 5 to infinity. Last thing here, okay, it's very similar to what you did with part A, except you're using a variable. Okay, everywhere we see a t, we're putting p plus 3 instead. Okay, so I'm going to go ahead and keep this function notation here. And that would look like p plus 3 squared, and then minus 5. Now, you could, in theory, square this by taking p plus 3 times p plus 3 to FOIL, but I actually like this version better. Because of those transformations of graphs, we could graph that more easily if we were trying to do that. Okay, so just leave it like that for me. You don't have to simplify that by expanding it out. If you have any questions, please feel free to come see me, okay?